Hello friends, in this session we will see voltage regulation of an alternator using EMF method. Note that this particular EMF method is also called as, there is another name to this, which is nothing but or synchronous impedance method. Synchronous impedance method. Getting my point? This is the second name to this particular method. Okay, now let us try to understand about this. We have already talked about that, all the mmfs which are there, those we will try to transform them into EMFs. Now we don't need those details here. Why? Because in order to you know to operate, or we can say, or to do the experiment on machine and then try to get regulation, we don't need that particular concept. So let us try to see how we can do the experiment and how exactly it is done, performed in your machine's lab, and then we will try to see calculations and observations regarding the same. Okay, yes. Now let us see what is regulation. Definitely we have talked about it a lot, like kind of percentage voltage regulation, nothing but what, EF minus Vt upon Vt. Yes or no? This is what we know. Multiply by 100 if you think of percentage. Out of this, what values you know? Out of this, you know Vt and Vt, correct or not? That will be given to you. Why? Because this is nothing but rated value or not. Yes, this is rated value, sir. We already know that because that will be mentioned on the nameplate of your alternator, correct or not? Yes. Now, what is that thing which you don't know is EF, correct or not? Now, who is there between Vt and EF? Definitely drops are there, yes or no? Because you know that, for example, if you consider it this way, for example, if you see that this is EF, then you think of this, drops, or something like that. Let me call this as ZS for this particular matter. Let me call this to be synchronous impedance ZS. Now here you must be having this plus or minus Vt, yes or no? Yes. And this is, for example, current IA. Let us consider now, between my EF and my Vt, who is present? ZS is present. Rather, IA ZS is present. Yes or no? Voltage drop of this particular impedance is present, which means I am interested into this particular ZS. Yes or no? Let me find this particular value of ZS. That is my important thing. That has to be my aim. Yes or no, dear? Yes or no, dear? Please tell me. Yes. Now, so in order to do so, what we want is, let us see, the first thing we have to do is we need some data. We need some data. What is the data we need? Let us see. First data you need is from OC test data or open circuit characteristics. OCC, open circuit characteristic, we say open circuit characteristics. This is what we need. Second thing what we need is SC test. What is SC test? SC test will give you some kind of SSC, short circuit characteristics. What are those? We will try to see them later, don't worry. Just focus on this parameter, short circuit characteristics. Then the third thing we need is the value of RA. Value of RA. Why? Because now if you see in this particular ZS, you definitely have reactance or not, RA. Yes, we have already seen that X by R ratio in case of alternator, it is going to be very very high. Yes or no? Yes. This means what? Resistance value is very very less, but you can definitely do that through experiments. That can be easily found out. How? We will try to see that afterwards. Okay, no problem. Now these are the three things you need, and then after that we can solve the sums and all. That's going to be very very cakewalk kind of. Okay, now what to do, how to find OCC characteristic and how to find SCC characteristics is our main intention. Okay, let us see what we can do is, for example, let me consider machines lab. You are in your machines lab for matter. Okay, academic purpose. If you see, let me consider that you are in your machines lab now. So this will be armature of the rotor, yes or no? Let me assume that it is of the stator, armature of the stator, right? Let me assume that it is going to be, let us say, star connected. Okay, let me have this to be star connected now. Yes or no? Now let me consider that this whole thing, this winding which is there, it is inside the yoke. Yes or no? This is going to be inside the yoke, correct? And at the center what you have is this neutral point. Yes or no? Now you please tell me, do you have access to this neutral point? Please tell me. No sir, we don't have any access to this particular neutral point. Yes, I know you don't have the access, correct or not? Yes. Now what I can do is, see, let me connect a voltmeter here, correct? And let me connect a ammeter over here, and then let me have three switches. Let me have switches over here. These are basically, if you see, these are nothing but TPST switches. What are they? Triple pole, what do we say, triple pole single throw switches. TPST switches they are, kind of. Anyways, don't focus on them, they are just switches. They'll do only closing and opening position, okay? Anyways, now if you see here, TPST and all, don't think about it, it's okay. And let me consider this to be this way, okay? And let me just short these terminals over here, just for fun, let us say. Now what can I do is, please focus, see, do you agree that here you will be having field winding? Yes or no? Yes sir. What will I do is, let me have a RF, let me connect a rheostat over here, okay? And let me just have this terminal over here, and then this goes here this way, kind of. And this is going to have definitely DC supply will be there. We have already seen that in our course, basic course, yeah? Yes. Now what is next? This is going to be plus, this is going to be minus, okay? Now first thing is, let us see what is open circuit test. Let us see what is open circuit test. Now in open circuit test, what you will do is, let me open this switch, let me keep this switch open like this. I'm not connecting any load to this, let me keep this open, okay? What will happen then if you keep this open? Now what will I do is, let me vary my field current. Let me vary my field current. How can I vary? From here, rheostat, no connection is there, which means what? Definitely field current. Field current in the sense current flowing through this field winding, let me call it to be IF. What will happen? What will happen now? For example, if you see, let me just draw this. What I can do is, let us say initially, when your field current is 0 ampere, let us see what happens. If your field current is 0 ampere, still you know that dipole alignment will not change instantaneously, kind of. Coercive forces and all will be there, kind of. BH curve and all, BH curve and all, you may try to see that, correct? Because for example, if you see BH curve, right? So BH curve is this way, right? So what will happen? There will be some residual magnetism left or not? Yes. Now because of that particular residual magnetism, see, even if this is open circuited, it's fine, no problem. What is happening is, because of that particular residual magnetism, will there be any EMF there? Yes, definitely there has to be some of the other EMF. So let me call that, that particular voltage that you measure through this is nothing but that voltage, which is nothing but VOC. Now if you see this voltmeter which is there, it is connected between what? Between one line and other line, yes or no? Between two phases or other two lines. So this particular voltage is nothing but line voltage, remember this point in mind. Now let us assume that that value is, let us say, 10 volts. For example, let me assume that value to be equal to 10 volts. Now what can I do is, I can definitely vary, what? My field current, yes or no? So for example, if I'm increasing my field current, rheostat has been moved to its minimum position, and now I'm increasing the field current by varying the rheostat. Now if my field current is increased, what will happen? We know that if my field current is increased, FF will increase, field MMF will increase, because of which what will happen? EF will increase, kind of. So open circuit voltage will increase or not? Yes, correct or not? So let me say that your field current, let us say, 0.1 ampere, and then for example it goes to 0.2 ampere, let us say 0.3 ampere, and so on, it just goes on. Yes or no? Yes. Now what happens is, your EF changes or not? Yes. Now your EF which changes, let us say that it changes like, kind of 20 volts, or you can say, let us say 50 volts, or 100 volts, and up to how many volts it will. For example, machine slab, if you see, machine slab if you see machine slab which is there, it is going to, 1000 here, this is 100 volts. You may get confused, so let me just, it is 100 volts, okay. And then at the end what we can have is, let us say 450 volts. 450 volts, let us consider that this is a rated voltage. Because see what should happen, because if you don't give rated voltage over here, means if you even more increase field current more than your rated voltage, what will happen? Insulation problems and all may occur. Anyways, don't think about them, it's okay. Now, OC test is always, because already we have discussed them in our transformers, correct? Yes. Now, if you think of OC test is applied. Now you have to go on varying field current, up to where? Till you get VOC to be equal to what? V rated. Yes or no? Yes. So let me consider that your V rated is, let us say, 450 volts. Now you please tell me, these are all line voltages or not? Yes. Now, do I need phase voltage here? Yes. Why? Because you know that in order to analyze equivalent circuit, we always use what? We always use phase, because that is going to be single line diagram. Single line diagram uses only phase, correct or not? Yes. So let me call VOC phase. What will happen now? Let us see. If it is VOC phase, then what happens? If you have got VOC line, VOC phase will be how? It is star connected. Star connected in the sense, we know that phase voltage is equal to line voltage by root 3. Line voltage by root 3. Yes or no? line, line voltage is already there, so by root 3, so 10 divided by root 3 you will get, you may get 20 divided by root 3, you may get 50 divided by root 3, you may get 100 divided by root 3, and so on. It just moves on up to 450 divided by root 3. Getting my point or not? Yes sir, this is nothing but the. Now what do you mean by OCC characteristics? Let us see. In the sense, if I have, let us say, this one, let us assume that this is a graph sheet. OCC characteristics will be what? Let me consider that on my x-axis I have got field current, and on my y-axis right now what I am having is going to be, let us say, VOC. Right now I am going to have VOC on this one. Okay. Yes. Now what happens? Let us assume that it is graph paper. Now what happened? As soon as my field current increased, what happened? Definitely my VOC increased or not? Yes. So VOC went on. So you got some observations there, correct or not? Some points of observation, and at the end you got this curve, kind of this curve you got, correct or not? This is nothing but OCC characteristics. Remember this thing in mind, very important, correct? Yes. Now let us see. OCC is done, only half data is done, sorry, 33.3% of data is done. You need SCC test also, no? SCC characteristics also. Let us see how you can get those. Now for example, now if I short this, okay. What happens when this gets short? What I will do is, the first step is what? There has to be some rated current or not of this armature. Rated current, will it be there or not? Will there be rated current for this armature? Please tell me. Yes sir, rated current will be there. Let me call that rated current to be equal to ISC, because this is happening at short circuit only, no? Here you have got complete dead short circuit on this, all the three lines. Yes or no? Yes. Now let us say that this ISC value is going to be 4.2 ampere. Let us say 4.2 ampere if you consider this value, because machines lab, small things we are analyzing, because machines lab approach, we are trying to see the things. So this is nothing but how much? 4.2 ampere. Yes. Now what happens? See, this ISC which is there, what are you supposed to do? See, the moment you short circuit this, you won't find this at all. Why? Because at that time, at initial case, IF will be 0. Now if you go on increasing IF, if you go on increasing, IF, go on increasing IF, at the end what you should get? Definitely ISC will also increase, correct or not? Yes. So what happens at some point at IF? At some point at IF, what happens is you get your ISC. So for example, at IF, let us say 0.4 amperes, at IF of 0.4 ampere, you get your short circuit current, which is nothing but rated current only. Getting my point or not? So can I say that in SC test, what you do, as soon as you vary your IF, what do you get? Please tell me. As soon as you vary your IF, what do you get? Definitely you can say ISC is going to be increased, so you are going to increase it up to what value? Rated value of that particular current. Yes or no? Otherwise what will happen? Conductor will melt. Yes or no? That is the reason, which is a problem, correct? Yes. So it is going to increase up to rated value. So basically what observations you have? You only have two values. What is that? First is rated current, and at what field current you get that particular rated current, which is nothing but zero point 0.4. So if you see in short circuit test, what happens? You get only two observations. What are those? IF at which ISC occurs. So IF is how much? For example, 0.4 ampere, correct? And for that ISC is what? 4.2 amperes. For example, let us consider this way. Now, will there be phase or line? Definitely it is going to be phase, but we know that in case of star connection, what we have, line current is nothing but equal to phase current or not? Phase current or not? Yes. Why? If you see this ammeter, whatever it is going to show you, you will have to trust that. So it is going to show you which value, line or phase? Definitely line value. Yes or no? Yes. So if ammeter is showing you line value, what does that indicate? What does that indicate? It indicates that line value is nothing but equal to phase value, that is nothing but short circuit current, problem solved. Correct? So you have got these two observations. In the sense, what has happened? 0.4 ampere and 4.2. So let me consider that somewhere here. Let me consider that somewhere here you have got this 0.4 amperes. Okay, somewhere here you have got this 0.4 amperes, and let us say somewhere here you have got this 4.2 amperes. So you'll say, sir, but here we have got VOC characteristics, no, on the top. Yes, that is the reason. What are we supposed to do is we may have to plot one more graph. One more graph, yes, but in the same graph paper on the same page. In the sense, let me just show that my y-axis at the same time also represents the currents. Yes or no? Yes. Now let me consider that that particular current is nothing but here, which is 4.2 ampere. For example, let me consider it that way. This is going to be y-axis. So what happens is at 0.4 you get this 4.2, no? So here this is the point, which means what? From 0 to this point you can have a straight line. Yes or no? You can have a straight line. Yes or no? Yes, sir. Short circuit, no, it is going to be SCC characteristics. Short circuit characteristic, basically no need to write characteristics again one time, but it's okay. Even if you write it's fine. Who is going to ask us? Now this is what we know. Now you have got OCC characteristic and SCC characteristics. Now the third required data is what? Third required data is you need RA. If you see OCC, OC characteristics already known. Yes, sir. SC characteristics already known. Now the next important thing is how to find RA. Now armature resistance, you can definitely calculate it by using multimeter. Yes or no? So what you can do is, because see inside terminals are not available with you, correct or not? So you can have multimeter from here to here. Let us consider multimeter from here to here, and you can measure the resistance. Yes or no? Yes. Now whatever resistance is this is RA only, correct? But this resistance is for what? It is for this whole circuit, this whole line, correct or not? This whole line, which means what? But I am interested in resistance of phase value, correct or not? Yes. So if you see, because this n, this neutral is not accessible to me outside, what I can do is, I have got these two or not, these two resistances or not, means I have got values of two resistances. Yes or no? Means from here to here, let us consider this as A, and let us consider this as B phase. So what will happen between this A phase and this B phase? You have got a resistance of these two values, so which is nothing but RE. Yes or no? So now what I can do is I can just simply divide this particular value by 2 such that I will get my RA. So my value of R is going to be what? R is going to be what? Definitely the multimeter reading, RA upon 2. Whatever value of resistance you find on that multimeter, just divide it by 2, you will get RA. That's it. Problem solved. So these are the three data that we have. Now let us see how you can solve the things, in the sense how you can find EF. That is the question. So in order to find EF, see RA you already have, you have OCC as well, you have got SCC characteristics as well. Let me consider, this is not SSC, this is SCC dear, please make the correction. This is going to be SCC, not SSC, it is SCC characteristic, because short circuit characteristic, circuit comes from C, correct? No, yes. Now if you see RA is what? Multimeter reading, RA given by multimeter reading, whatever you have, that you just divide by 2, you will get armature resistance RA. Now what I will do is, next step, at this point you have got, when 0.4 ampere field current was there, at that time you have got 4.2 ampere of armature current or short circuit current or rated current, correct or not? So now I am interested in what is the voltage at the same point on the top. This voltage I am interested into, and let me call this voltage to be VOC, correct? Now from these two readings, because now I have got value of VOC and ISC already, you know, because it is rated current only, no, that is mentioned on the nameplate already. So what is, let me divide VOC and ISC. What is VOC by ISC? Definitely it is impedance or not? Yes sir, it is going to be impedance, because voltage upon current is impedance, volts per amperes. So if it is impedance, which is in ohms, it is not just an impedance, it is rather synchronous impedance. This is the reason we say that EMF method is a synchronous impedance method. Getting my point? Yes. So this is going to be VOC upon ISC, which is this. So from this, what do you get? You get ZS or not? Yes. Now RA value do you have already? Yes, because now if you see, what is Z? Z is nothing but what? ZS is what? RA plus J times X. Correct or not? RA plus J times XS. Synchronous reactance. What is XS? Synchronous reactance. We have talked about it earlier as well, no? Yes, this is going to be ZS, which is RA plus JXS. Now, what can you do? ZS is there. Definitely. ZS is nothing but what? Under root of what? What we have? RA square plus XS square. Yes or no? Yes. RA square plus XS square. Now, if you square on both sides, what do you get? You get ZS square is equal to RA square plus XS square. But then, what are you interested in? RA square value you already know. ZS square value you already know. You want XS square. So XS square is going to be what? ZS squared. If you keep this RA squared on the other side, you get minus RA squared. Now, if you just keep under root, what will happen? Under root will come here, and this 2 is gone because of that under root. Because of under root on left hand side. So this 2 is gone. So you have got this synchronous reactance excess, which is equal to ZS squared minus RA. Synchronous reactance excess is found out. Now next step is what? To find EF, because that is what is our aim, because we have seen that ER is very very variable. That is the reason we want something which has to be constant, which is nothing but EF, correct or not? Yes. Now if you see EF, definitely phase values only dear, please remember this, all are phase values. Now EF in generalized, if you see in case of transformer also, we are seeing the same formula. What is that? Of no load voltage, what is that formula? This is the formula. What is that? VT. Or in case of transformer, we had here V2, correct? So VT cos phi plus IARA the whole square plus VT sin phi plus IAXS the whole square, correct or not? This is the way, for example, if it is there. Now from this is going to be plus minus here, remember this is going to be plus minus. I'll tell you what you have to do. VT value already you know, because that will be given on the nameplate, correct? IA value is what? IA is nothing but rated armature current, so that value you already know. RA value you have already found out, yes or no? RA by 2, that particular value, whatever you got, means multimeter reading divided by 2. That's it. That is nothing but RA. So RA is also known. VT is known. IA access square. Now see here, IA access square is access known. Yes. Now just we have known about access. Now just we have come to know about access. What we do? We had got that OCC characteristic. We have got SCC characteristics. Now what we do? You please map that particular point which is there on the SCC characteristics, and you can just plot it above. If you plot it above, whatever voltage you get, that is going to be VOC, and that VOC divided by ISC is going to be synchronous impedance. From that synchronous impedance, if you know value of RA, which you have already calculated through experiments, right? So what do you have then? You will have value of EF, which is nothing but equal to what? Under root of VT cos phi minus IA squared. Yes or no? Yes. Now, if you see here, how to get values of cos phi and all, how to get value of cos phi and all. If you see, we have already discussed about it that it is very very desirable to give power factor rating as well in case of alternator. Yes or no? That is the reason power factor will be given. If cos phi is known, definitely you can find phi. If phi is known, definitely you can find sin phi. That's it. That is going to be very very easy. Next important thing is what? This is plus or minus, right? So the plus sign you are supposed to use when it is lagging, and minus sign you are supposed to use when it is leading. Yes or no, dear? Yes. So that's it. Now from this you get value of this EF per phase or EF phase value. Now you please put that in the formula. What is voltage regulation? Voltage regulation is equal to EF minus VT by what? VT into 100. That's it. If you think of percentage of voltage regulation, this is going to be it. Yes or no? Yes. Now what do you see now? See, this particular method. Now there are some important points which you need to understand about this particular method. First important point is that this particular method is called as pessimistic approach. Pessimistic method. Correct or not? Yes. The next is what? This is going to be pessimistic approach. Why? Because let us see. Pessimistic in the sense, what happens is whatever reading of voltage regulation you get here, it is going to be more. Correct? And what does this mean? What do we mean by pessimistic method? Pessimistic method in the sense, whenever we see that there is some person who is pessimistic, what will he do? He will try to find faults in every person. Yes or no? Similarly, even if voltage regulation will be less, this will show you a more greater value of voltage regulation. This is the only disadvantage of this EMF method. But in most of the practical cases, we do prefer EMF method over any other methods because it is kind of easy only. Correct or not? Yes. So now once EF is got, you can just simply replace it here in EF minus VT by VT. Yes. And another thing is, remember, if you think of the voltage regulation in phase, then this EF also has to be in phase, and this VT also should be in phase. This VT should be in phase. VT should be in phase. Remember this. Getting my point? Yes. Now after this, immediately we will try to solve some problems based on this EMF method. Thank you.